All right, so the first type of surface that we're going to study, and one of the most simple examples of a surface, is the idea of a plane. So conceptually, what should a plane be? Well, a plane is something that's flat, let's say. So here's an example of such a thin object. So flat surface, looks like a sheet of paper in three-dimensional space. So qualitatively, we have a flat surface, but how do we actually describe that mathematically? So in other words, is a question, what relationship between our coordinates, x, y, and z, will describe a plane. So how do we think about this? So we have to try to think mathematically, what does it mean for this surface to be flat? Well, we talked about this idea of a normal vector. And if we look at, let's look at a couple normal vectors at points on the surface. So if I pick this point here, a normal vector would look maybe something like that. I could pick another point, maybe say right here. What would a normal vector there look like? Well, something like that. I could pick another point, let's go down here. And I could say, well, what does a normal vector there look like? Something like this. So in our curvy surface, all of these normal vectors looked a little bit different, but look at these ones. All of these normal vectors are parallel to all of the other normal vectors. And so we really want to try to figure out a way to mathematize this. When we're talking about vectors being parallel or perpendicular, we want to talk about, well, really parallel and perpendicular in the context of vectors. So we can talk about these vectors that I've drawn on the picture as being parallel to each other, but how do we talk about one of these vectors being perpendicular to the surface? Well, so here's a way that we can think about it. So if we have a normal vector, n, so I'll label one of these guys n, and just to make things better, we can say, we'll say that the components of this are a comma b comma c. And let's say we also have a point p0. We'll just say that we have some x, some y, and some z. And so we'll call this this point here p0. Then we can say the plane with normal vector n through p0 will consist of all points x, y, and z such that, well, such that what? So here's another point on the same plane. And if I have 2 points, I actually can very easily make a vector that goes between the two of them by just starting, say, at p0 and extending to that point. Now, that vector lies on the plane. The normal vector n that I drew right here is perpendicular to the plane, so it has to be perpendicular to that vector on the plane. If I pick a different point on the plane here, I can make a vector that starts at p0 and extends there. And this normal vector also has to be perpendicular to it. So I can write down one of those vectors. We stop at x, y, z, so the vector can be found pretty easily by just the usual way that we find vectors between 2 points. So maybe I'll label this x, y, z. And I'll label this P0 here as x0, y0, z0. So if we find the vector between those 2 points, we get this. And we just said that this vector n, which is ABC, should be perpendicular to it, which we can describe by saying that the dot product between these guys is 0. And the nice thing when we do that is we can now just explicitly compute this dot product. And what we're going to get when we do that is the following equation. So this is an algebraic relationship that is going to give us the equation of a plane that has a given normal vector that passes through a given point.